Okay, so adding and subtracting radicals, the idea was what? We need like radicals. In this case, square root 2 are like radicals. So we can add the numbers, they're called coefficients, outside, kind of called coefficients. 5 plus 3 is 8, so we get 8 root 2. In the next example, square root 20, square root 5 are not like radicals. So we have to simplify the square root 20, which becomes square root 4 and square root 5. Why did we use the 4, Ian? Good, because we can square root it. I wouldn't split this into 10 times 20 or 1 times 20, because that's not going to do you any good. It's got to be the 4 because it has a square root. Square root of 4 is 2. So now we have 2 root 5 plus 5 root 5, or 7 root 5. The root 5s are like radicals, so we can add together. 2 plus 7 is 9. Right? What about the next one? Now I'm jumping into cube roots. We could do this with 4th roots or 5th roots too. Try to simplify the cube root of 54. What would I look for? Cody? Okay, we want to look for the cube roots numbers, right? So looking at your cube root list, does 1, 8, 27, 64, do any of those numbers go evenly into 54? 8 doesn't go into 54 evenly, but 27 does. If you take 54 divided by 27, you get 2. This is the square root of 27 multiplied by, I just said square root, sorry, cube root of 27 multiplied by the cube root of 2. The cube root of 27 is just 3, so now we have 3 times the cube root of 2, and then bring down our other radical minus cube root of 2. Some of you might want to think about this as like a 1 cube root of 2 for this second term. If we have 3 cube root 2's minus 1 cube root 2, we have 2 cube root 2's. And then that's simplified because the 2 inside the radical cannot be simplified any further. Okay, any questions on that so far? That's just adding on to the number part that we did with the first part of the lesson. Okay, in the next set of notes, this is going to be really important. Change this x to an n. Inside the radical, it says x raised to the 2n. It wouldn't make any sense if it was an x. So, right, looking at this, I just gave you a little bit of notes here. If you take the nth root of something raised to the n, you just get that number back. Think about taking the square root of x squared. The square root and the square sort of undo each other. If I take the cube root of x to the 3rd, that's also going to just be x. One way to prove it to yourself, now that we know about rational exponents, is that x, if you're taking the cube root of x to the 3rd, it's the same as x to the 3 over 3, and 3 divided by 3 is 1. And so that's sort of why this works. Okay? But you're not going to have any really that simple. We're going to be looking at, well, what if your exponent inside is larger than your exponent outside? Is there a way to take some of those variables out of the radical? And there are. With this one, because we have like 2n on the inside and n on the outside, n can divide into this 2n twice. And so really what we have is x squared. Just kind of watch a few. On this next one, the 5th root of x to the 5th, just x. 5 goes into 5 one time. That's the way I like to think about it. On the next one, 5 goes into 10 2 times, so we just get x squared. So the square root, it's basically we are square rooting this number. So the long way to think about this is that x to the 10 is the same as saying x to the 5th times x to the 5th, because 5 plus 5 is 10. And then if we 5th root each of those, the 5th root of x to the 5 is x. The 5th root of x to the 5 is x again. So we have an x and an x on the outside now because we've used the 5th root. It disappears once you've used it, if that makes sense. So here we're going to use the cube root, but this is not going to go in evenly, right? We're going to have 3 goes into 10 3 times with 1 left over. So the way you write it is this: y to the 3rd, but we still have a cube root of y inside the radical. You're really thinking about like rational exponents. 10 divided by 3 is 3, with 1/3 left over, which is why you have a y to the 1/3 technically here. Does that make sense? Yes or no? We'll look at some more. Okay. They start to get a little more complicated, but treat each variable separately and it's okay. X with the 5th root by x to the 7th. So 5 goes into 7 one time with 2 left over. So this is going to be x to the 1 on the outside, but 2 left over on the inside. We're going to make a 5th root here, but I'm leaving some space because I know I have 3 variables. For the next one, 5 goes into 8 one time with 3 left over. So this will be y to the 1 on the outside with 3 left over on the inside. The next one, 5 goes into 10 exactly twice. So this will be z squared on the outside. And then you're done. Does that make sense? Okay, good. All right, example 3. Cube root of 216. Now that one's not a variable, so we just use our number chart. 216 does have a cube root. If you look at 216 on our chart, it's 6 to the 3rd is 216. So this part becomes 6 on the outside. Let's leave some space in case we have x and y that are going to come out, and I'm going to write my cube root symbol because I'm probably going to have stuff left inside. 3 goes into 9. So we're working on the x here. 3 goes into 9 exactly 3 times, so x to the 3rd. But then 3 goes into the 5 only once with 2 left over. So we have y to the 1 on the outside and y squared left inside. And then we're simplified. Some people, you might want to put like a times sign in here just to show that it does get a little confusing. It looks like the 3 that belongs with the cube root might be an exponent on the y, and it's not. So if you want to put that extra time sign in between, just so it doesn't look like z to the 25, like for this one. Okay. There's 3